In this video, we will cover solving exponential and logarithmic equations, as well as what common logarithms are and natural logarithms. The common logarithm is a logarithm with a base of 10. When you see a log without a base listed, we are assuming that it is base 10, and this is referred to as a common logarithm. You may use a calculator to find values of the log of 1,000, the log of 42, and the log of 0.005832. Calculators use base 10. There's also a natural logarithm, which is a logarithm with a base of e. To avoid confusion, we use slightly different notation. We use ln instead of log. ln is meant to convey that our logarithm has a base of e. So the natural log of x is equivalent to the log base e of x. We can use a calculator to find the values of the natural log by using the ln key on our calculator. So the natural log of e to the third power is equal to 3. The natural log of 142 and the natural log of 0.005832 all have values that you can find easily on a calculator. If there are bases other than e and 10, most calculators will not be able to handle that. Some will. So we have what's called the change of base theorem that allows us to choose any base we want. As a reminder, a, x, and b have to be positive real numbers, so they can't be 0 and they can't be negative. A can't be 1, and in this instance, b can also not be 1. If I have the log base a of x, and I don't want it to be in base a, I can pick any base I want and find the value of the log base a of x by using the log base b of x divided by the log base b of a. So for example, in this log base 5 of 17, most calculators can't calculate log base 5, but we can use the log base 10, or we could use the log base e. We've arbitrarily chosen to use natural logs. So the log base 5 of 15 is equal to the log e of 17, in other words, the natural log of 17, divided by the natural log of 5. Now, as long as you input this in your calculator, you don't actually need to come up with the 2.8332. You do need to be careful with parentheses, however. Most of the time, we round our answers to 4 decimal places, or perhaps 3. Be careful and watch your directions for what decimal place to round your answers to. Now, this property that we're looking at here allows us, along with the definition of logarithms, to solve equations. As long as x, y, and a are greater than 0, so they don't equal 0 and they're not negative, and a is not equal to 1, then the equation x equals y is equivalent to the log base a of x equals the log base a of y. In other words, if a single non-log term is equal to a single non-log term, then I can say the log of that term, x, is equal to the log of the other term, y. So one of the strategies we're going to use is if my problem has a log base a of m equal to n, then I'm going to use the definition to solve that. I'm going to rewrite that logarithm in exponential form. So if I have a single log on one side, I will rewrite this expression or this equation in from logarithmic form to exponential form, and that will oftentimes allow me to solve. On the other hand, if I have a single logarithm equal to a single logarithm, then I can use that property that we just saw. I can basically drop the logs. Single log equals a single log. It's important that it's a single logarithm equal to a single logarithm for this property to apply. Now, the vice versa of that property, if I have a single term equal to a single term, no logarithms at all, then I can again use that property to take the log of both sides. So I have no logarithms, but I can take the log of both sides, which oftentimes allows us to solve a problem. Here's example 1. 7 to the x power equals 12. There are no logarithms in this problem, so we'll use the property that says x equals y if and only if the log of x equals the log of y. So we're going to take the log of both sides. Because we're going to end up using a calculator, you want to use log base 10 or log base e. In other words, a common log or a natural log. We're just choosing to use the natural log. So we take the log of both sides. Now, the reason this is helpful is because I can use the power property to bring the x down in front of the logarithm, and it's no longer an exponent. The natural log of 7 is a value, is some decimal value. So we will isolate our x value by dividing both sides by the natural log of 7. And now I have 1.277 as a value for x. Here's another example. We have e to the x squared for our exponent equals 200. There are no logarithms here. So I'll use the property that says x equals y if and only if the log of x equals the log of y. We can use any log we want. We could use the log base 10. However, it's advantageous to use the natural log because our bases are the same. The natural log of e to the x squared is just equal to x squared. So now we have x squared equals the natural log of 200. I'll square root both sides. And remember, there are two roots, plus and minus. And I get approximately plus and minus 2.302. Here's another example. 7 times the natural log of x equals 28. So I have a logarithm on one side, but I don't have it on the other side. Now, I wouldn't say that there's a single logarithm yet because that 7 is being multiplied by the natural log of x. So the first thing we want to do is divide by 7. Now I have a single logarithm on the left-hand side and a term on the right-hand side. I'm going to use the property of the definition of logarithms. I'm going to rewrite this in exponential form. So e to the fourth power is equal to x. And I can leave my answer like that. I don't need to give a decimal value for that. Here's another example. The log base 2 of x to the third power minus 19 equals 3. Now here I do have a single logarithm and a single non-logarithm on the opposite side. So like the previous example, I'm going to use the definition of logarithms. I'm going to rewrite this exponentially. So 2 to the third power equals x cubed minus 19. Now since we're solving for x, we want to get x all by itself. So we will add 19 to both sides and then cube root. So x is equal to 3. In this example, you see logarithms all over the place. What we don't have is a single logarithm on the left-hand side. We do have a single logarithm on the right-hand side. So right now it's not in the proper format. In order for us to use the property or the definition, we need single logarithms. So is there a way to combine the log of x plus 6 minus the log of x plus 2? Sure. There is the property that tells us I can turn that into a quotient. And now I have a single logarithm on the left-hand side equal to a single logarithm on the right-hand side. So the logs go away. I can drop the logs. Now I'm going to multiply both sides by x plus 2. And I'm going to end up with a quadratic equation. It factors. I set each factor equal to 0, and I get two answers. Now you have to be careful with your two answers. The definition of a logarithm is that you cannot take the log of 0 and you can't take the log of a negative number. So if you replace in the original problem, if you replace x with -3, will you be taking the log of a negative number? Well, it turns out yes, you will. If you put -3 in this log of x plus 2 part, you're going to be asked to take the log of -1, which you cannot do. So x equals -3 is not a proper answer. The only answer is x equals 2. Here's another example. I've got a single logarithm on the left-hand side. It's big, it's got a lot of stuff to it, but it is a single logarithm, and a non-logarithm, a single term on the right-hand side. So we'll use the definition of a logarithm. That is, we're going to rewrite this in logarithmic form. 2 to the third power equals 3x minus 7 times x minus 4. Now we have a problem like we saw in chapter 1, which is just solving a quadratic equation. Does 3x squared minus 19x plus 20 equal 0 factor? It does. 3x minus 4 and x minus 5. Set each factor equal to 0 and check your answer. You cannot take the log of a negative number. If you place 5 in place of x, will you be taking the log of a negative number? No, you won't. If you use 4/3 in place of x, will you be taking the log of a negative number? It turns out the answer is no in both cases, so we can use both 4/3 and 5. In this case, I have two logs added together equals a single term. So I don't have a single logarithm equal to a single logarithm. I don't have a single logarithm equal to a single term. But I can change that form. I can use the product property and combine those two logarithms into the log of 3x plus 2 times the log of, or times just x minus 1. Now something they did, they turned the number 1 into the log base 10 of 10, which is fine. Now I've got a single log on one side equal to a single log on the other, so I can drop the logs. And again, I have a quadratic equation to solve. Does 3x squared minus x minus 12 factor? It doesn't factor, so we have to use the quadratic formula. Now we also need to check to see if both of these answers work. Does 1 minus the square root of 145 all over 6 give us the log of a positive value both times or not? Does 1 plus the square root of 145 over 6 give us the log of a positive value when we plug it into both logs or not? It turns out 1 minus the square root of 145 over 6 gives us a negative value, so we cannot use the first solution. So the solution is 1 plus square root of 145 over 6.